What if an invisible force secretly controlled every step humanity takes into space? Gravity quietly governs the universe, yet most people barely notice its influence daily. Every rocket launch, orbit, and landing depends on mastering gravity's relentless pull. Without understanding gravity, space exploration would collapse into chaos and failure instantly. Humans have always been fascinated by the mysterious force pulling everything downward. From falling apples to orbiting planets, gravity shapes motion across unimaginable distances. Early scientists struggled to explain why objects fall and planets stay in motion. Then Isaac Newton introduced a revolutionary idea about universal gravitation. He proposed that every object attracts every other object with measurable force. This simple concept transformed how humanity understood the structure of the universe. Suddenly, the same force causing falling objects governed celestial bodies in space. Gravity was no longer mysterious magic, but a predictable and calculable phenomenon. This discovery laid the foundation for centuries of scientific progress and exploration. Space exploration began as a dream, but gravity defined its limits immediately. Escaping Earth's gravity became the first major challenge for any space mission. Rockets needed immense power to break free from Earth's strong gravitational grip. This requirement led to engineering innovations never seen before in human history. The idea of leaving Earth required both courage and precise scientific understanding. Engineers calculated how much force was needed to overcome gravitational resistance. This calculation became known as escape velocity, a critical concept in astronautics. Without reaching escape velocity, spacecraft would fall back toward Earth inevitably. Achieving this speed demands enormous fuel consumption and advanced propulsion systems. Early rocket pioneers experimented endlessly to understand these complex requirements. Their failures taught valuable lessons about gravity's unyielding control over motion. Eventually, humanity succeeded in launching objects beyond Earth's atmosphere successfully. The launch of Sputnik 1 marked a historic breakthrough in space exploration. It proved that humans could overcome gravity and place objects into orbit. Orbiting Earth requires balancing forward motion with gravitational pull perfectly. Too slow and the object falls. Too fast and it escapes completely. This delicate balance demonstrates gravity's constant influence on spacecraft trajectories. Astronauts in orbit appear weightless, but gravity is still acting upon them. They are actually in continuous freefall around Earth, creating the illusion of weightlessness. This phenomenon fascinates scientists and inspires curiosity among people worldwide. Understanding orbital mechanics became essential for planning long-duration space missions. Space agencies invested heavily in studying gravitational interactions between celestial bodies. Missions required precise calculations to ensure spacecraft reached their intended destinations safely. Even a small miscalculation could result in mission failure or total loss. Gravity also assists spacecraft through a technique known as gravitational slingshot maneuver. This method uses a planet's motion and gravity to accelerate spacecraft efficiently. It allows missions to travel farther using less fuel than traditional methods. This clever use of gravity demonstrates human ingenuity and deep scientific understanding. Space exploration is not about defeating gravity, but learning to work with it. Every mission carefully plans how gravity will influence its path and speed. Without gravity, planets would drift aimlessly and orbits would not exist. Gravity creates structure and stability within the vast emptiness of space. It binds galaxies together and keeps stars and planets in predictable motion. For explorers, gravity is both an obstacle and a powerful tool simultaneously. Mastering this force opens possibilities for reaching distant worlds and beyond. Early missions focused on orbiting Earth and understanding nearby gravitational effects. Later missions expanded toward the Moon, requiring new calculations and strategies. The success of Apollo 11 showcased humanity's ability to navigate gravitational challenges precisely. Astronauts had to escape Earth's gravity and then enter the Moon's influence. This transition required exact timing and flawless execution of complex maneuvers. Returning to Earth involved yet another careful interaction with gravitational forces. Each phase demonstrated how deeply gravity shapes every aspect of space travel. The moment a rocket ignites, gravity immediately begins resisting every upward movement. This resistance is not gentle, but a powerful force anchoring everything to Earth. Engineers must design rockets strong enough to fight against this invisible barrier. Every kilogram added to a spacecraft increases the challenge of escaping gravity. Fuel becomes the lifeline that determines whether a mission succeeds or fails. The heavier the spacecraft, the more fuel is required for liftoff. This creates a constant struggle between efficiency, weight, and mission objectives. Scientists carefully calculate how much thrust is needed for each launch. These calculations are rooted deeply in Newton's laws of motion and gravitation. Even a tiny miscalculation can prevent a spacecraft from reaching orbit. Rockets must accelerate rapidly to overcome Earth's gravitational hold effectively. This acceleration creates intense pressure and forces on both structure and crew. Astronauts experience extreme physical stress during these critical launch moments. Their bodies are pushed back as gravity and acceleration combine dramatically. Yet, this intense phase lasts only a few minutes before conditions change. Once in orbit, the relationship with gravity transforms into something fascinating. Instead of resisting gravity, spacecraft begin working in harmony with its pull. Orbiting becomes a delicate dance between speed and gravitational attraction. This balance allows spacecraft to circle Earth without falling back immediately. The concept may seem simple, but execution requires extraordinary precision always. To maintain orbit, spacecraft must travel at incredibly high horizontal speeds. These speeds ensure they keep missing Earth while constantly falling toward it. This continuous falling creates the illusion of floating or weightlessness on board. Astronauts often describe this experience as both surreal and breathtakingly beautiful. However, gravity still plays a crucial role even in this state. It keeps the spacecraft bound to Earth and defines its orbital path. Without gravity, there would be no orbits, only endless drifting in space. Space agencies constantly monitor orbital paths to avoid dangerous collisions. Satellites, debris, and spacecraft all share this crowded orbital environment. Gravity ensures they follow predictable paths, but risks still remain significant. Small adjustments are often required to maintain safe and stable orbits. These adjustments use onboard thrusters to correct deviations caused by various factors. Even atmospheric drag at high altitudes can slowly alter orbital paths. Engineers must account for these subtle influences during mission planning stages. Gravity also varies slightly depending on altitude and Earth's shape. This variation affects how spacecraft move and how calculations are performed. Precision becomes the difference between mission success and catastrophic failure. Beyond Earth orbit, new gravitational challenges begin to emerge gradually. Spacecraft traveling farther must deal with the gravitational pull of other bodies. The Moon becomes the first major target, requiring advanced gravitational understanding. Missions must calculate how to leave Earth's influence and enter lunar orbit. This transition zone is complex and requires perfect timing and alignment. A mistake here could send spacecraft drifting endlessly into deep space. Scientists use mathematical models to predict these transitions with high accuracy. These models are based on centuries of accumulated scientific knowledge. Johannes Kepler contributed laws describing planetary motion that remain essential today. His work helps explain how objects move under gravitational influence in space. These principles guide spacecraft as they travel between celestial bodies efficiently. Gravity is not just a barrier, but also a guiding force. Skilled navigation allows spacecraft to use gravity to their advantage. This marks a shift from fighting gravity to mastering its potential. Deep space missions depend entirely on this advanced understanding of motion. As missions grow more ambitious, gravitational calculations become increasingly complex. Computers now handle simulations that humans once calculated manually. These systems predict trajectories with incredible accuracy and reliability. Still, human expertise remains vital in interpreting and refining these models. Unexpected variables can always challenge even the most precise calculations. Space remains an unpredictable environment despite all technological advancements. Gravity continues to be both a challenge and a powerful ally. Every successful mission proves humanity's growing ability to understand and harness gravity. What if gravity could actually help spacecraft travel faster instead of slowing them down? This idea seems surprising, yet it powers some of humanity's greatest space missions. Scientists discovered that gravity can be used as a natural accelerator in space. This technique is called a gravitational assist or slingshot maneuver. Instead of burning fuel, spacecraft borrow energy from moving planets. This allows them to gain speed without carrying massive additional fuel supplies. The concept transformed how humans explore distant regions of our solar system. Early missions relied heavily on fuel, limiting their reach significantly. But gravitational assists opened doors to previously unreachable destinations. The idea requires precise timing, positioning, and deep understanding of motion. A spacecraft approaches a planet and enters its gravitational influence carefully. As it swings around, the planet's motion transfers energy to the spacecraft. This interaction increases speed and alters direction in a controlled way. It's like being pulled forward by a moving object in perfect synchronization. One of the most famous examples is the Voyager 1 mission. This spacecraft used multiple gravitational assists to travel across the solar system. It visited Jupiter and Saturn while gaining incredible speed from each encounter. Without gravity assists, such a mission would have been nearly impossible. The same strategy helped Voyager 2 explore even more distant planets successfully. These missions demonstrated the true power of understanding gravitational dynamics. Gravity became not just an obstacle, but a pathway to exploration. Engineers now design missions specifically around planetary alignments. These alignments determine when gravitational assists are most effective. Sometimes missions must wait years for the perfect planetary positions. Timing becomes just as important as technology in these complex journeys. Missing a launch window could delay a mission by decades. This highlights how deeply gravity influences planning and execution in space exploration. Gravitational assists are not random, but carefully calculated interactions. Scientists simulate these maneuvers using powerful computers and detailed models. Every angle, speed, and distance must be predicted with extreme accuracy. Even minor errors could send spacecraft off course permanently. The success of these maneuvers proves humanity's growing mastery over physics. It also shows how nature itself can be harnessed intelligently. Spacecraft effectively steal a tiny amount of momentum from planets. This does not affect the planet noticeably due to its massive size. Yet the impact on the spacecraft is dramatic and mission-changing. Gravity also helps slow down spacecraft when approaching distant destinations. Without slowing down, spacecraft would simply fly past their targets. Missions use planetary gravity to reduce speed and enter orbit safely. This is especially important for missions to Mars and outer planets. The Mars Reconnaissance Orbiter used gravity and atmosphere to stabilize its orbit. This process is known as aerobraking, combining gravity and atmospheric drag. It reduces fuel needs and increases mission efficiency significantly. Gravity continues to shape every phase of deep space travel. Even interplanetary trajectories depend entirely on gravitational calculations. Spacecraft must follow curved paths determined by gravitational forces. Straight lines rarely exist in the dynamic environment of space. These curved paths are called transfer orbits, carefully designed for efficiency. One common example is the Hohmann transfer orbit used widely. It provides the most fuel-efficient route between two circular orbits. Such techniques rely entirely on understanding how gravity influences motion. The deeper humans travel into space, the more complex gravity becomes. Multiple celestial bodies can influence a spacecraft simultaneously. This creates regions of instability and unpredictable motion patterns. Scientists study these regions to avoid risks and find opportunities. Some areas, like Lagrange points, offer unique gravitational balance. At these points, forces cancel out, allowing stable spacecraft positioning. Missions like the James Webb Space Telescope operate near such locations. This allows them to remain stable with minimal fuel consumption. Gravity once again proves to be both complex and incredibly useful. Mastering it allows humanity to extend its reach across vast distances. Each mission builds upon previous knowledge and refined techniques. The universe becomes more accessible as our understanding deepens. Gravity is no longer just. Could gravity actually bend time itself and change reality in space exploration? This surprising idea reveals how deeply gravity affects the universe beyond motion. Gravity does not only pull objects, it also influences the flow of time. This concept comes from Einstein's groundbreaking understanding of space and time. Massive objects like planets and stars distort space-time around them significantly. This distortion affects both movement and the passage of time itself. Near stronger gravity, time actually moves slightly slower compared to distant regions. This phenomenon is known as gravitational time dilation in physics. It might seem impossible, but experiments have confirmed it with precision. Even satellites in orbit experience tiny differences in time compared to Earth. These differences must be corrected for accurate navigation systems on Earth. Without these corrections, GPS systems would quickly become unreliable and inaccurate. Gravity therefore plays a hidden but critical role in modern technology. Space exploration depends heavily on understanding these subtle time variations. The theory of relativity explains this relationship between gravity and time. It completely changed how scientists view the structure of the universe. Instead of separate forces, space and time are now unified. Gravity is understood as curvature in this combined space-time fabric. Spacecraft traveling through space follow these curved paths naturally. Their motion is guided by space-time geometry rather than simple force alone. This understanding is essential for planning deep space missions accurately. Even interplanetary navigation requires accounting for relativistic effects. Without these corrections, spacecraft could miss targets by huge distances. Precision becomes extremely important when traveling millions of kilometers. Scientists continuously refine models to include gravitational time effects. These improvements help missions achieve higher levels of accuracy and safety. Gravity also influences communication between Earth and distant spacecraft. Signals traveling through gravitational fields experience tiny delays. These delays must be considered when controlling space missions remotely. Every second matters when coordinating complex interplanetary operations. As spacecraft move farther away, gravitational influences become more varied. Different planets and stars create overlapping gravitational effects in space. This creates a dynamic environment full of constant changes. Engineers must predict how these variations affect spacecraft behavior. Advanced simulations help visualize these complex gravitational interactions. These tools are essential for mission planning and risk reduction. Gravity also shapes how astronauts experience time during missions. Although differences are tiny, they become meaningful over long durations. Long-term space travel requires careful synchronization with Earth time. This ensures astronauts can return without major temporal mismatches. The International Space Station experiences continuous gravitational and time-related effects. Astronauts aboard it age slightly differently than people on Earth. These differences are extremely small but scientifically significant. They confirm that gravity directly affects time in real conditions. Space exploration constantly tests these theories in practical environments. Each mission provides new data about gravity's hidden influence. This data helps refine our understanding of the universe further. Gravity is no longer just about movement, but also about time. It connects physical motion with the structure of reality itself. This dual influence makes gravity one of the most powerful forces. Space missions must consider both physical and temporal effects simultaneously. Ignoring either aspect could lead to mission failure or errors. Gravity also affects how light travels across space. Light bends slightly when passing near massive objects due to gravity. This effect helps scientists observe distant galaxies and stars. It acts like a natural lens in the universe. These gravitational lenses reveal objects otherwise hidden from view. Space telescopes rely on this effect for deeper cosmic observation. Gravity, therefore, becomes a tool for exploring the farthest reaches. It shapes not only spacecraft paths, but also what we can see. Every discovery in space science is tied to gravitational behavior. Understanding gravity unlocks deeper layers of cosmic reality. It connects motion, time, and light in a single framework. The universe operates through this invisible yet powerful structure. Mastering gravity means mastering the true nature of space, and what if the future of space exploration depends entirely on mastering gravity perfectly? Humanity now stands at the edge of a new cosmic revolution. Gravity continues to shape every ambition for interplanetary and interstellar travel. Future missions will rely on deeper understanding of gravitational physics. Scientists are now exploring ways to manipulate gravitational forces indirectly. These innovations could redefine how spacecraft travel across vast distances. Instead of fighting gravity, future systems may fully harness its potential. Advanced propulsion systems are being designed with gravity in mind. These systems aim to reduce fuel dependency dramatically. Space travel could become faster, safer, and more efficient than ever before. Artificial intelligence is now helping predict complex gravitational environments. These systems analyze massive data to improve mission planning accuracy. The universe presents countless gravitational challenges waiting to be understood. Each new mission expands humanity's knowledge of these invisible forces. The dream of reaching other star systems depends on gravitational mastery. Even interstellar travel must account for complex gravitational interactions everywhere. Scientists are studying hypothetical propulsion methods like gravity manipulation concepts. Though still theoretical, these ideas inspire future generations of engineers. Understanding gravity at deeper levels could unlock unimaginable possibilities. Spacecraft may one day ride gravitational waves across the universe. These waves are ripples in space-time caused by massive cosmic events. Their discovery opened a new window into understanding the universe. The gravitational waves confirmed Einstein's predictions about gravity's dynamic nature. This breakthrough changed how scientists study cosmic events dramatically. Gravity is no longer seen as static, but constantly evolving. Massive collisions between black holes create detectable gravitational waves. These signals travel across space, carrying information about distant events. Observatories on Earth can now detect these subtle cosmic vibrations. This allows scientists to hear the universe in a new way. Gravity becomes a messenger carrying stories from deep space. Future space missions may use these waves for navigation. This could revolutionize how spacecraft move through deep space. Humanity may one day surf gravitational currents across galaxies. Such ideas once seemed science fiction, but are now researched seriously. The boundaries between imagination and reality continue to blur. Gravity remains the key to unlocking these futuristic possibilities. Every discovery pushes the limits of human understanding further outward. Space agencies are investing heavily in next-generation gravitational research. International collaboration is essential for tackling these complex challenges. The Artemis program aims to return humans to the Moon. It also prepares humanity for deeper space exploration beyond lunar orbit. Gravity plays a central role in planning these upcoming missions. Lunar gravity offers unique opportunities for scientific experimentation and learning. Future Mars missions will require even more precise gravitational calculations. Landing and returning from Mars depends entirely on gravitational navigation. Engineers are designing systems that adapt to multiple gravitational environments. These systems must function across Earth, Moon, and Mars conditions. Gravity becomes a constant companion throughout every stage of exploration. It influences travel, landing, survival, and return journeys. Without mastering gravity, interplanetary civilization would remain impossible. Humanity's future in space is deeply tied to this invisible force. Each step forward requires better understanding of gravitational interactions. The universe continues to challenge scientists with its complexity, yet every challenge brings new breakthroughs and discoveries. Gravity connects all celestial bodies in a unified cosmic system. It binds galaxies, shapes orbits, and guides cosmic evolution. Space exploration is ultimately a journey through gravitational landscapes. These landscapes define how everything in the universe moves. Humanity is slowly learning to read and navigate them. This knowledge transforms how we view our place in the cosmos. Gravity is both a limitation and a gateway to exploration. It challenges us while also enabling our greatest achievements. The future of humanity lies in understanding this universal force. Every mission brings us closer to mastering gravitational science. The story of space exploration will always begin. Imagine a future where humans travel beyond galaxies using gravity itself. This vision begins with understanding gravity not as barrier, but guide. Every discovery in space exploration brings humanity closer to cosmic mastery. Gravity remains the silent architect behind every movement in universe. From smallest particles to largest galaxies, everything obeys its influence. Scientists continue pushing boundaries of gravitational knowledge every single day. Space exploration has transformed gravity from mystery into powerful navigation tool. Future spacecraft may use gravity like ocean currents for travel. This would allow journeys across space with minimal energy consumption. Such breakthroughs depend on decades of research and innovation. Humanity's curiosity continues driving exploration beyond known frontiers. Every mission expands understanding of gravitational behavior in extreme conditions. Black holes represent strongest gravitational forces known in universe. Studying them helps scientists test limits of physical laws. The black hole shows how gravity can reshape space itself. Nothing, even light, escapes their immense gravitational pull. These cosmic objects challenge our understanding of reality completely, yet they also reveal secrets about universe's deepest structure. Gravity near black holes becomes unpredictable and intensely powerful. Scientists use advanced instruments to study these extreme environments carefully. Each observation helps refine theories of gravity further. Space telescopes continue capturing data from distant gravitational phenomena. These discoveries inspire new generations of physicists and engineers. Gravity remains central theme in all cosmic exploration efforts. Even dreams of colonizing other planets depend on it. Human survival beyond Earth requires mastering gravitational adaptation strategies. Future habitats must be designed considering different planetary gravities. Mars, Moon, and Earth all present unique gravitational challenges. Engineers are already developing solutions for long-term space living. Gravity affects human health in space environments significantly. Muscle loss and bone density changes occur in microgravity conditions. Understanding these effects is essential for long-duration missions. Medical research continues addressing gravity-related human adaptation issues. Space agencies are preparing astronauts for extended deep space travel. The journey to Mars represents next major gravitational challenge. Every phase of mission depends on precise gravitational control. Landing, living, and returning all require careful planning. Gravity also influences communication delays across vast distances. These delays shape how missions are controlled from Earth. Future technologies may reduce these limitations significantly. Humanity's relationship with gravity continues evolving rapidly. What once seemed impossible is now becoming achievable reality. Space exploration is rewriting our understanding of physical laws. Gravity is no longer limitation, but powerful scientific opportunity. Each breakthrough reveals deeper layers of universal structure. Scientists now view gravity as a bridge between theory and exploration. This bridge connects human curiosity with cosmic reality. The universe becomes more accessible with every discovery made. Gravity guides spacecraft, shapes planets, and defines existence itself. It is the invisible thread connecting all cosmic phenomena. Future generations will rely on gravitational mastery for exploration. New technologies will emerge from understanding this fundamental force. Humanity may one day travel between stars effortlessly. Such future depends entirely on continued gravitational research progress. The story of space exploration is still being written. Gravity remains its most important and constant character. Every mission adds new chapter to this ongoing story. The universe continues to reveal its secrets slowly. Humanity's role is to observe, learn, and explore. Gravity will always guide us through the cosmic journey. It challenges our limits while expanding our possibilities. Space exploration is ultimately a dance with gravity. This dance defines our past, present, and future in space. The universe invites us to understand its deepest force, and gravity is the key to unlocking that infinite journey.